Let's go ahead and get started. I assume the roll sheet has migrated around or is in the process of doing so. So today we're going to be talking about open loop op amp circuits. So an open loop op amp circuit is a circuit that does not contain a feedback path that connects the output terminal of the amplifier to one or both, which we'll see a situation where we have feedback to both terminals on Friday, of the input terminals. And I'll draw an example of an open loop op amp circuit here. So starting with my op amp, here's my non-inverting input terminal denoted by V plus. Here's my inverting input terminal denoted by a V minus. My output terminal denoted by V out. Going to make my power supply connections just real quick. So here's VCC plus, and here is VCC minus. So for an open loop configuration, I might have something like this where I just throw a practical voltage source connected to one of my input terminals. I'm going to choose to do it to my non-inverting input terminal here. So here's R sig in series with some signal generator V sig. I'll ground my inverting input terminal and I'll drive some load with my output voltage like so. Oh, and I forgot that minus sign there. So hopefully this circuit looks a little familiar because it's literally the one that we analyzed in Monday's class because today is Wednesday. I think, yeah, okay. So when we analyze this particular circuit in our last lecture, we figured out that outside of a very small range of input signal voltages, the output voltage signal would saturate to either VCC plus or VCC minus, which means that unless we're trying to amplify extremely small microvolt scale signals, an open loop op amp circuit isn't particularly good at creating an undistorted output signal. So instead, we use open loop op amp circuits in a lot of control systems applications like threshold detection and signal processing applications like crossing detection and analog to digital converters. So we're going to focus largely on application today. Okay. So the first application of an open loop op amp circuit that I want to talk to you guys about is the non-inverting comparator. So a non-inverting comparator is used to compare the strength of an input signal. So particularly it's looking at the voltage of the input signal, and it is going to compare it to some reference signal. And then it is going to generate a specific output depending on what the result of that comparison is. Okay. So we could use something like this to say turn on a warning light if an output voltage gets too high, or if our signal generator was like a thermal sensor that generates a voltage depending on the temperature. This could be an indicator light that says, hey, don't touch the stove right now. It's still hot, which is literally what's part of your stove. Okay. So the non-inverting comparator circuit, I'm about to draw it, is essentially the exact same thing I drew up here, except that we are going to include a reference voltage. Okay. So I'm going to start with my op-amp circuit, or the op-amp portion of the circuit here. So once again, we've got V plus, V minus, V out, our supply voltages, VCC plus and VCC minus. As I mentioned a moment ago, we might drive some kind of indicator light as our load. So I'll put this as RL here. We're going to put our reference voltage, which will be a DC voltage usually, and connect that between our inverting input terminal and ground. So I'm going to call this guy Vref, and then we're going to put our signal generator between our non-inverting input terminal and ground. So here's R sig and B sig typically as a function of time. Okay. We're going to use the following parameters for analyzing how this guy behaves. And then we're going to generalize things after this. Okay. So our source parameters are that our signal voltage is going to range anywhere from 0 volts is less than V sig is less than or equal to 5 volts. And our signal resistance, R sig, is going to be 10 kiloohms. Down here below, I'll put our supply voltages. So we'll have VCC plus will be equal to positive 5 volts. VCC minus, bless you, will be negative 5 volts. And lastly, our reference, which would be supplied by, at least in this case, another DC power source. We'll talk about that in a little bit. We're going to have a reference voltage of 2 volts here. Our op-amp parameters. We're going to have an open loop voltage gain of 10 to the 5 volts per volt. An input resistance of 1 mega ohm and an output resistance of 25 ohms. So using the same op-amp as we used in our last class meeting. And lastly, we're going to have the following load parameters. And let's just say that we're trying to drive a bulb that has a resistance of about 100 ohms. So we're going to analyze this circuit, which means that we need to convert this representation into using using the practical op amp model like we did in class on Monday. So this will be another little bit of practice. So whenever I'm redrawing any of these circuits, I start by drawing my practical op amp model. So here's my V plus pin. This resistor is going to be my input resistance. So I'm just going to go ahead and put in that this is 1 mega ohm. This is going to be my V minus pin. And my differential voltage VD is always defined as the difference between V plus and V minus. So it goes right here. Now I'm kind of drawing the output side of things. So this is where I'm going to have AVOL times VD. So that's just going to be 10 to the 5 times my differential voltage. This is going to be in series with my output resistance of 25 ohms. So I've drawn the practical op amp model part of this guy. Now I'm going to start making my external connections, right? So between my V minus node and ground, I need that voltage source Vref, so it'll go right here. Between my my non-inverting input terminal and ground, I will have V sig in series with R sig. So something like this, where I'm still just going to label this guy V sig since it can change values. We'll talk about that in a moment. This is going to be that 10 kilo ohm signal resistance. On the output side of things, I should connect that load resistor between the output terminal and ground. So here's 100 ohms, and lastly, I'm going to label the voltage drop across that load resistor as the V out that I'm interested in. Okay. So what we're going to do is kind of use voltage division here really quickly with V sig as a variable to get an understanding of how this guy is going to behave, right? So, oh, and I guess this Vref, I'll just write it over here, would be 2 volts. Okay. So using voltage division, we should be able to see pretty easily that our differential voltage is going to be whatever V sig is minus 2 volts, our reference voltage. So just to be clear here, what I'm doing is I'm making what I hope to be the simple observation that the voltage V sig is in series with the voltage Vref, but they are of opposite polarities, so they will subtract from each other, right? If I just follow my way around that left-hand loop, if I start from the bottom left-hand corner, I see the negative polarity terminal of V sig, those 2 resistors, and then the positive polarity terminal of Vref. So that's going to look like V sig minus 2 volts. And then I'm going to multiply that by my voltage division relationship. Since I'm trying to find the voltage drop across Rn, that means I'm going to have the 1 mega ohm resistor here on top, and then 10K plus 1 mega ohms in series. So that's what my differential voltage is going to look like. And then my output voltage, V out, is going to be my open loop voltage gain. So 10 to the 5 volts per volt times my differential voltage, V sig minus 2 volts times 1 mega ohm over 10 kilo ohms plus 1 mega ohm. And since I'm finding the output voltage, this is going to be another application of voltage division. So I'm going to have a ratio of resistances here where the 100 ohm resistor that I'm trying to find the voltage drop over is in the numerator. And then the denominator, I'll have my R out, which is 25 ohms in series with my load resistance of 100 ohms. So if I were to plug in any given value of Vsig into either of these expressions, I could find both my differential voltage and my output voltage based on these. Okay? So we know that the maximum possible output voltage in this case is going to be 5 volts. And the minimum or most negative possible output voltage in this case is going to be negative 5 volts because our supply voltages are plus and minus 5 volts. So what I'm going to do is I'm going to use the fact that V out is a known quantity to figure out what the maximum value of our signal voltage can be before it causes saturation and what the minimum value of our input voltage can be before it causes saturation, right? So for an output voltage of V out is equal to 5 volts, what we would find, and do you guys want me to write down all of the math here or just give you the result because this is a one equation, one unknown system?
Just the result.
Just the result, okay? V sig will be greater than or equal to 2.00006,313 volts. So I'm just going to make a note here, approximately 63 microvolts above Vref. And similarly, for an output voltage of V out is equal to negative 5 volts, we'll see that V sig will be less than or equal to 1.9993688 volts, which is approximately 63 microvolts below Vref. So we have a voltage plus or minus 63 microvolts around V sig to where we actually get amplification. Anything beyond that, we are saturating to one of our power supply voltages. Okay. So from this, we can say that our output signal V out will essentially be VCC plus or positive 5 volts whenever our signal voltage is greater than Vref. I'm not putting greater than or equal to because when it is extremely close to Vref, it won't actually be VCC plus. It might just be Vsig. Okay. And it'll be VCC minus whenever Vsig is less than, once again, just less than, not less than or equal to Vref. So this is the behavior of a non-inverting comparator. And I want to show you guys really quickly how we could set up a non-inverting comparator circuit in LT Spice, just to verify that this is indeed how it behaves. So the first thing that I'm going to put on my schematic diagram is my op amp. So I'm going to click on the component menu. And there are lots and lots of op amps that we could choose. Okay, so I'm going to click on this op amp menu right here, and we'll see that there are literally hundreds of different op amps that we have to choose from. Because this particular program is made by Analog Devices, it has practically all of the op amps that they make. It used to be so Analog Devices bought out Linear Technologies, which is what the LT and LT Spice stands for. So you'll see if we scroll over here that there's a ton of linear technology amplifiers also available to us. And then I think Maxis or Maxon, I don't remember exactly which one it is, but they pay to have their models already included in here as well. We're not going to use any of those. We're going to use a universal op amp, okay? So there are several different universal op amp options that we could use. So I just want to talk about what the difference between some of them are. So universal op amp 1 says that it is a linear single pole op amp with no internal nodes or output voltage range limits. So this is definitely not one that we want to use because it's not going to take into account saturation distortion, okay? Universal op amp 1 is literally the same thing. Universal op amp 2 is a single pole op amp with one internal node. It has limitations on the slew rate, which is how fast the output can change when the input signal is changing. It has an output voltage and current limit. So this is the one that we're probably going to use. But the later stages are essentially just universal op amp 2, except that you can parameterize more different things, right? So I'm going to click on universal op amp 2. I'm going to place it down here. And for the most part, we're going to be able to leave it alone, but I do want to show you a couple of things here. So if I have my mouse placed over this model and I right click, it gives me these parameters. So my open loop voltage gain, it says, is 1 meg. So that is 10 to the 6. Ours is actually only going to be 10 to the 5. So if I click on this, I can change it from 1 meg to 0.1 meg, and it actually more closely matches what we've got. I'm not going to mess with this gain bandwidth product because that's not going to really have any impact on what we're doing since we're not dealing with like high frequency systems. I'm not going to change the slew rate. I'm going to leave this current limit at 25 milliamps, not for any particular reason. Um, I can change the input resistance here. So we said that it was going to be 1 mega ohm, so I'm just going to change that to 1 mega ohm. For whatever reason, LT Spice's model doesn't have an output resistance that you can change. That's handled by changing that output current limitation. But we're just not going to bother with that. Okay. So I've made this op amp as close to the parameters that we're dealing with as possible. Realistically, it wouldn't have made a whole hell of a lot of difference if I didn't. I just wanted to show you that that's something that we could do. I do want you guys to notice that this op amp, when I dropped it on here, it put the inverting terminal on top and the non-inverting terminal on bottom, but it put the positive power supply terminal on top and the negative power supply terminal on bottom. So if we want this to have the positive the positive input terminal on top, let me remember what I do to just select it. Sorry, this looks a little different than my normal one. Let me just do this one. Grab it to move it, and I'm going to press Control M. I thought that would mirror it. So R rotates it. Control E mirrors it. Okay. So I rotated it twice to flip it upside down, but facing the wrong direction. And then I did Control E to mirror it so that it looks right. Okay. Don't have to do this. We could have just, handled it with a inverting input terminal on top and a non-inverting input terminal on bottom, but I just wanted to show you this. All right, so I'm going to leave this alone and then I'm just going to move it over here and I'm going to play around with stuff. So we could make all of our connections on that particular op amp as it's drawn, but I find that to be cluttered and annoying. So what I'm going to do instead is I'm going to set up all my supply voltages on the left-hand side of my circuit. So I'm going to start with two voltage sources, and I'm going to kind of just stack them on top of each other, like so. I am going to tie the negative polarity terminal of the one on top to the positive polarity terminal to the one on bottom. And then I'm just going to put a center node here, and I'm going to put ground at this center node. Okay. So I'm literally setting this up like a dual channel power supply, like how you would to set up a physical op amp circuit. Okay. Um, since our positive supply voltage is 5 volts, I'm going to put this guy as 5. And since our negative supply voltage is negative 5 volts, and this might be a little bit weird, I'm going to put this as positive 5 as well. The reason why I'm putting this one as positive 5 is because I'm saying that the negative terminal is going to be 5 volts lower than ground, which is negative 5 volts. If I wanted to put this as negative 5, I'd need to rotate that power supply thing there twice, and I just don't feel like doing that. So if I have it this way where they're just both on top of each other, I put 5 on both, and this is going to give me plus and minus 5. Okay. I'm going to go ahead and make my other supply voltage, which is going to be my reference voltage. And over here, I'm going to drop another voltage, and this one is going to serve as my input voltage. Okay. So the first thing I'm going to do is ground the negative polarity terminals of both of these guys, and then I'm going to set these up. So my reference voltage is 2 volts, so that's fine. This guy's going to be my input voltage, and it needs to range from 0 to 5. There are a couple of different ways that we can do it. I'm going to do it in what I believe to be a lazy way. I'm going to go into the Advanced tab, and I'm going to turn this into a sinusoidal voltage. Okay. So I need this to range from 0 to 5. So I'm going to give it a 2.5 volt DC offset. So now it's going to range from 2.5 plus or minus what the amplitude is. And so I'm going to make that amplitude also 2.5. So now it's going to go from 2.5 minus 2.5, which is 0, to 2.5 plus 2.5, which is 5. And so that's giving me the total range that I want. For the frequency, I'm just going to say that it's going to be 1 hertz. So it's going to do 1 cycle every 1 second. And I'm going to leave everything else alone. Okay. Now what I'm going to do is I'm going to label a bunch of these networks. Okay. And actually, I'm going to give myself little stubs of wire here first, and then I'm going to label networks. So let's see. Oh, I also had 2 resistors to take into account. So let's go ahead and take care of that. So this is going to be a 10 kilo ohm resistor right here. This is my signal resistance. Kind of running out of space. So I'm just going to move this over again, just to pretty things up. And I need to put a load resistance around here. So this is going to be a 100 ohm resistor. Let's ground this. Wire this. Okay. So coming back over to these supplies. I'm just going to label one as VCC plus up here. And then I'm also going to pull that VCC plus and apply it here. Okay. So what this is doing is it's saying, hey, whatever voltage is here, just apply that voltage here without actually having to connect up all the wires and stuff so that our schematic diagram isn't as cluttered. Okay. I'm going to do the same thing for VCC minus. Hold on just a second. So here's VCC minus as the network label. I'm just going to drop this here so that it's saying, hey, the voltage at this node is labeled as VCC minus. And shit, accidentally put that there. And I'm going to do the same thing over here. and just drop this guy here. And now it's saying the voltage at that node is minus 5 volts. Let's see, I'm going to do one for VREF. So put it here and here. I'm going to do one for VN here and here. And lastly, I'm going to do one for V out. And now I'm going to simulate this thing. So I'm going to go into my simulation command. I'm going to do a transient analysis. I'm just going to run it for, let's say, 5 seconds for the sake of running it for 5 seconds. Realistically, running it for 1 second should give us all the information we need, but it'll be fine. And I'm going to press play. And I'm going to look at my input voltage. So I could click either at this node to get my input voltage or at this node. It's going to be the same thing. So I have my voltage that's ranging from 0 to plus 5 volts and back, right? And now I'm going to look at my output. And what I should expect to see, based on the analysis that we did, is whenever my input voltage is above 2 volts, my output voltage should be 5 volts. And whenever my input voltage is below 2 volts, my output voltage should be negative 5 volts. So if I click on V out right here, it's not giving me exactly what I would expect. I wonder if it's because of that 10 kilo ohm resistor is limiting some current. Let me do something real quick just to see. No, maybe it's my load resistor. This guy might be drawing too much current based on my limitations. There we go. Yeah. So I needed to mess with the current limiting thing there. Let me see if I can just put that 10K resistor back in just for the hell of it. And volts. Yeah. So 5 volts over 100 ohms is 50 milliamps. So restricting it to 25 milliamps is what was causing that distortion. So let me just go in here and just say that this thing can do up to 100 milliamps just for the hell of it. And then put that 100 ohm resistor back in and just verify that it works the way that I want it to. Hot damn. Yeah. So it's not quite hitting 5 and it's not quite hitting -5. Again, it's because of the current limiting stuff, but it's close enough for my intentions here. If I just bump that larger. Okay. Well, it's just going to do its thing, but it's close enough to 5 and -5 like we would have expected there. Okay. So it's just a limitation of the computer model in this case. Okay. So it is behaving effectively how we would expect it to, but there's a better way that we can actually see this. Okay. So like right now, my input signal and my output signal are plotted as a function of time. Ashton, yes.
Uh, can, can you show us how to run it again? Like what buttons to press?
So this guy right here with the gear is how I configured things. This guy right here is how I ran the simulation itself. So let me close this out and just rerun the simulation.
So wait, it just yeah.
Yep. Transient gives us the signal as a function of time, which is what we were looking at. Okay. I'm putting a stop time of 5 seconds so that I get 5 cycles. It's more than I need. And I'm running it. And then I'm looking at V in which I just clicked on this node with V in with the voltage probe, and I'm looking at V out, so I'm clicking on this node V out with the voltage probe as well.
That's it.
Okay, I'm bored, so I'm going to move on. So what I'm going to do now, instead of looking at things as a function of time, is I'm going to show you how to look at V out as a function of V in, because that's probably a useful thing to be able to look at as well. Okay. So if I right click on this graph and no, excuse me. If I mouse over the X axis and I right click on that, it tells me that I'm plotting against time. That's not what I want to plot against anymore. I want to plot against Vn. So what I'm going to type down here is V, open parentheses, Vn. And what this is doing is it's plotting against whatever voltage that node has. Okay, so it's just going to do the full range of those voltages. And it gives me a kind of funny looking graph here, and I'll explain that in a second. So this green line right here, notice that it's 0 volts when Vn is 0 volts, and it's 5 volts when Vn is 5 volts. This is Vn versus Vn, so it just has a slope of 1. That is completely and utterly useless information to us. So I'm going to remove that guy, okay? So what we can see here, we look at this guy, is that, hey, whenever Vn is less than 2, it looks like it's mostly down here. And whenever Vn is greater than 2, it's mostly up here, okay? There's some slope here. This is just the number of time steps, and it's like sometimes catching spots where there is a linear relationship, okay? And the reason why it's got so many lines is because we're doing from 0 to 5 times. So if we only did from 0 to 5 one time, so if I change my simulation command to do it for just 1 second and run it, I only get this one nice line because it just does it once. Okay. So this is the behavior that we were expecting. And just for the hell of it, if I erase this resistor right here, because it's the one that's causing it to act a little bit wonky, we now see that it's pretty much the -5, the +5 centered around 2, like we would expect. Okay. Okay. So now let's talk about the non-inverting comparator. Excuse me, the inverting comparator, because we've already talked about the non-inverting comparator. So we're not going to go into as much detail on the derivation side of things here because I feel that it's largely unnecessary, and you'll see why in a moment. So the circuit for the inverting comparator is going to be almost exactly the same thing as the circuit for the non-inverting comparator. So I've got my op amp here. Here's the node V plus, V minus, V out, my supply voltage, VCC plus, my supply voltage, VCC minus. we might be driving some load. So the only difference between the inverting comparator and the non-inverting comparator is I'm just going to swap the terminals where I apply my input signal and my reference voltage. So before we had our reference voltage on the V minus pin, so now I'm just going to put it on the V plus pin. And then I'm going to put my signal generator on the V minus pin. So here's R sig in series with some voltage, V sig. And let's say that all parameters are the same as the previous example. So I want you guys to use a bit of intuition and tell me, if you can, what you think is going to happen, or what you think the results of swapping where we apply VSig and where we apply VREF, what's that going to do?
Yeah, we're gonna invert it.
Flip the output. So we have this thing, that equation up there. It's literally just going to change replace VSig with VREF and VREF with VSig. That's it. Okay. So I'm just going to put using intuition. This particular circuit will have an output of VCC plus when VSig is less than VREF, and it will have an output of VCC minus when VSig is greater than VREF. And we can very easily verify that in our LT SPICE model by just deleting that where it says VSig and deleting where it says VREF on the input side of the op amp and just swapping those two guys around and running the simulation again. And we will get this behavior. Okay. So this is our inverting comparator. So let's take this a step further. We're going to do a design example together. So I want us to design an analog to digital converter. Okay, so I'm going to write this out here really quickly. An analog to digital converter, or ADC, is a device used to convert analog signals into digital signals. We are going to design a circuit such that any input signal greater than 3 volts generates a digital high, which will be 5 volts at the output. And any input signal less than 3 volts generates a digital low. Or 0 volts at the output. So let's talk our way through this.
Yeah, supposed to be like VCC minus, is that sign supposed to be greater than, or is their goal supposed to be less than?
Say that again?
What is it? Less than for the V out there?
Oh, right here. No.
It should be greater than V, right?
Yeah. Okay. Sorry about that.
You said greater than.
I said greater and then wrote down less than. My apologies. Yeah. It should be literally the opposite of what we had previously. Yeah.
So you essentially want like just a flat DC signal?
So if, coming back to this design example,
Yeah.
okay. So yes, so if the output signal, excuse me, if the input signal is greater than 3, I want the output to be a flat 5 volts. And if the input signal is less than 3, I want the output to be a flat 0 volts. So the first question is, does this require an inverting or a non-inverting comparator? Because we are comparing our input signal to 3 volts and then generating an output based on that comparison. So this is absolutely a comparator application here. Okay. So inverting or non-inverting comparator. Non-inverting comparator. Why?
When goes greater.
We want the output to go high. Yep. So we want the output to go high when the signal is greater. So that is non-inverting comparator behavior. Okay. So I'm going to start by drawing my op-amp circuit. Okay. Plus, minus, here's V out. Okay. So we want our input signal to be applied, since we're dealing with a non-inverting comparator, we want our input signal Vn to be applied on the non-inverting side of the amplifier. Okay. All right. So what should our reference voltage be in this case?
3 volts.
3 volts. So I'm just going to write that by putting a 3 volt right there. Okay. So the only other thing I have left to figure out is what my supply voltages need to be. So what should my positive supply voltage be? 5 volts, because we want our output to swing to 5 volts whenever our input is greater than 3. And what is our negative supply? So I'm just going to ground that guy. Okay. So we've done a design problem here. Okay. And just to verify that we get the behavior that we want, we're going to throw this into LT Spice real quick. So I think the only thing that I'll really need to change is the reference voltage, and then just getting rid of those extra resistors, since I'm not really dealing with any of that stuff.
Yeah.
So there's Vn, there's Vref. This needs to change from 2 to 3. And if we run this, we see whenever our input signal is greater than 3 volts, it saturates to 5. Whenever our input signal is less than 3 volts, we're saturating, excuse me, to -5. So I should change this guy down here to 0. My apologies. Rerun. Yep. So we get the exact behavior that we want. So There isn't anything particularly wrong with this design, other than the fact that we kind of need three DC voltage sources to do it, right? So I'm saying three sources because I'm saying VCC minus might be a source. In this case, it was ground. There's a different way that we can establish our reference voltage that doesn't require the use of a dedicated power supply, which would be a lot more cost efficient because the cost of a DC power supply can be expensive. Okay. Um, or another way to put it is if our op-amp circuit was ran off of a battery, we wouldn't want to have a different size battery just to serve as a reference voltage or something like that. So let's investigate how that might work. Okay. So what kind of circuits do we know about that allows us to take some known voltage and shrink it down to some smaller voltage?
Voltage divider.
A voltage divider, okay? So we are going to use a voltage divider network in order to establish a resistor biasing network, okay? So let me hide this. So I'm going to call this subsection here resistor biasing to establish VREF. So I'm going to draw essentially a modified voltage divider network, okay? The reason why I'm drawing what I'm calling a modified voltage divider network is because we have two known voltages that we have to deal with, right? VCC plus and VCC minus. If VCC minus is ground, we can get away with just the simple voltage divider that we're used to, okay? So here's the network that we're going to look at, okay? So I've got some resistor R1 connected in series with VCC plus. In this branch, I'm going to have some resistor R2 in series with VCC minus. And I'm going to say that our reference voltage is just the voltage drop across this portion of the network with respect to ground. So I know that this is drawn in kind of an obtuse way, but this is trying to indicate that V reference will always be between VCC plus and VCC minus, depending on what values of resistors that we choose. Okay. So in order to figure out what our relationship is, I'm going to employ superposition to make this really easy. Because if I use superposition where I only leave one supply voltage on and leave the other supply voltage off, this is literally just a normal voltage divider circuit, okay? So we should be able to see from this that our reference voltage with VCC plus on is going to be VCC plus times R2 over R1 plus R2. So that's the contribution of VCC plus. And I'm going to add to this VCC minus times R1 over R1 plus R2. So this is the contribution of the VCC minus power supply voltage to the overall output voltage. Okay. So simple voltage divider network that we can use to establish any voltage between VCC plus and VCC minus, depending on what we choose for R1 and R2, okay? Nothing particularly wild or crazy there. Now, what I want to explore, and we've only got 18 minutes to do this, so I might need to hurry things up a little bit, is do the size of the resistors matter? Meaning we're dealing with ratios of resistors here, but does the size of any individual resistor particularly matter? And the short answer is yes, okay? So for the previous example problem where we had VCC5 was equal, VCC plus was 5 volts, VCC minus was 0 volts, and VREF was 3 volts, we could use this relationship to find, so let me just write this. For the ADC example, where VCC plus was 5 volts, VCC minus was 0 volts, and VREF was 3 volts. This relationship gives us, so our reference voltage was 3 volts, it will be equal to VCC plus of 5 volts times R2 over R1 plus R2 plus 0 volts times, it doesn't matter, right? So we can say pretty easily then that the ratio of R2 over R1 plus R2 has to be equal to 3 over 5. Everybody catching what I'm throwing there? A little bit of algebra, right? So we could redraw our ADC circuit as something like this. So here's my op amp. Here's my output voltage. Here's V plus. V minus. And what I'm going to do up here on the top is I'm going to put a positive supply rail. Of 5 volts, and I'm going to connect that to the VCC plus pin. And on the bottom, I'm going to have a negative supply rail for ground. And I'm going to connect that to my VCC minus pin. I could label that as ground as well. I'm trying to make this as generic as possible so that it's pretty obvious what you would do if you didn't have a 0 volt negative supply and all of that kind of good stuff. Okay. So my input signal source is connected to my non-inverting input terminal. So I'm just going to sneak that guy in right here. Just put V in as a function of time. Actually, let me do this a little bit better because I want to show you guys something here. I'm going to put an R sig in series with it, just in case that's the case that we actually have. Okay. And now I'm going to set up that voltage divider network. So that's just going to be connected between here and here, where this node point is essentially establishing our reference voltage. This is the resistor R1, and here is the resistor R2. So mathematically speaking, any resistor combination of R1 and R2 that results in this ratio of 3/5 should work, right? So to me, that means that um, let's say if R2 is 3 ohms and R1 is 2 ohms, that works. Or if R2 is 3 kilo ohms and R1 is 2 kilo ohms, that works. If R2 is 3 mega ohms and R1 is 2 mega ohms, that also works because any of those meet the criteria. But what I want to see is what the impacts of having those various values of resistor actually have on our behavior. Okay. So I'm going to use the practical op-amp model and redraw just the input side of this circuit. Okay. The output side is well defined, so I'm not going to worry about that too much. Okay. So using the practical op-amp model, looks like this. Okay. So here's my input resistance for my op amp, right? And all of the previous examples, we've used an input resistance of 1 mega ohm. That's what I'm going to continue to use here just for illustrative purposes, okay? So that's where that 1 mega ohm is coming from. And this is my voltage VD, okay? So between the non-inverting input terminal and ground, I have my signal resistance, which we've been using 10 kilo ohms for this today. So that's what I'm going to use. And then I've got my signal source here, V sig, and that's currently there. This node is just going to get extended over here to the left, and I'm establishing my voltage divider network. So up here, I had my resistor R1. Down here, I have my resistor R2, and it's between that node where VREF is and ground. And then I've got a 5-volt supply, so I'm just going to put that over here on the left. So this is one way that we could represent the input side of this network. Okay. So before I move on from this, is everybody okay with how I've drawn this, or does anybody have any questions? Okay. So what I'm attempting to illustrate here is that if we choose resistors that hit our ratio, but we make a poor decision as to what the size of those resistors are, we're actually going to see that our reference voltage is going to drift as our input signal changes, which is a very bad thing because we're trying to compare that input signal to our reference voltage. So we're going to look at, actually, I'm going to apply KCL to this network here really quickly. So I'm just going to be adding this current plus this current plus this current together. And I'm going to wind up solving for the reference voltage. Okay. Yeah, and we'll see that in just a moment. Okay. So if I apply KCL at that node, so KCL at reference node, what I'm going to have is VREF minus 5 volts over R1 plus VREF over R2 plus VREF minus V sig over what's essentially Rn plus R sig, but I'm just going to write this down as 1 mega ohm plus 10 kiloohms is equal to 0. And we're going to look at two cases here. We might talk about a third one very briefly as time permits. So in our first case, we're going to say that R1 is 2 mega ohms and R2 is 3 mega ohms. So as a sanity check, do these resistor values give us the voltage divider ratio that we're looking for? 3 over 2 plus 3 is indeed 3/5. So I would say yes. So the issue is that when V sig is equal to 0 volts, then we would have Vref minus 5 volts over 2 mega ohms plus Vref over 3 mega ohms plus Vref minus 0, so just Vref over 1.01 mega ohms is equal to 0. And if we solve that equation for Vref, we'll find that Vref is 1.371 volts, which is pretty damn far away from the expected value of 3 volts that we were trying to get with that voltage divider ratio, right? Similarly, when V sig is equal to 5 volts, so this is the maximum value of our range that we're looking at, then we would have Vref minus 5 volts over 2 mega ohms plus Vref over 3 mega ohms plus Vref minus 5 volts over 1.01 mega ohms is equal to 0. And solving this for Vref, we wind up getting 4.086 volts. Again, a pretty significant distance away from our desired reference voltage of 3 volts. Okay. So if we have these resistors that are comparable to the size of the input resistance of the op amp, we introduce a significant amount of error into our system because what we are expecting with this voltage divider network, if we scroll back up here, is that it's being loaded by something like an open circuit. So something having a very, very large input impedance. So if we use resistors that have a similar resistance, we are not meeting that criterion. The op amp network doesn't look like effectively an open circuit. And so we see a significant amount of fluctuation in that reference voltage. So let's contrast that with choosing kilo ohm size resistors. Okay. So in our second case here, we're going to say that R1 is equal to 2 kilo ohms and R2 is equal to 3 kilo ohms. And we're going to run the same parameters, right? So when V sig is equal to 0 volts, we're going to wind up having Vref minus 5 volts over 2 kilo ohms plus Vref over 3 kilo ohms plus Vref over 1.01 mega ohms, that branch to the input of the op amp does not change, is equal to 0. And this gives us a reference voltage of 2.996 volts. So it's not perfectly 3 volts, but it's pretty damn close to 3 volts. Very similarly, when Vsig is equal to 5 volts, then we would have Vref minus 5 volts over 2 kiloohms plus Vref over 3 kiloohms plus Vref minus 5 volts over 1.01 mega ohms is equal to 0. And so we'll have, solving this, we'll get Vref is equal to 3.004 volts. So again, not exactly 3, but really, really close. Okay. So it looks like the smaller that we make those resistors, the less that our reference voltage will drift. So this begs the question, we're just going to talk our way through this because we only have a minute left of class. Could we use 2 ohms and 3 ohms? Technically, yes. The reason why we wouldn't want to necessarily use 2 ohms and 3 ohms is because that's going to cause a large amount of current to flow through that voltage divider network, which just means we're wasting energy, right? So it meets the design criteria, but it's not a practically good design because it's just burning a bunch of energy for no reason, right? So 5 volts over 5 ohms of resistance means that we're going to be drawing 1 amp of current. And so that means that that 2 ohm resistor is going to be absorbing 2 watts of power, and that 3 ohm resistor is going to be absorbing 3 watts of power, which means we need very large, beefy, and expensive power resistors. Whereas if we use the kilo ohm size resistors, the current's going to be on the order of milliamps. So we can use very cheap, quarter watt or an eighth watt rated resistors that you can get for a nickel, right? So we get a marginally better electrical performance by using really, really low resistors, but the cost of those components is tens to hundreds of times more expensive than if we use kilo ohm size resistors. So generally speaking, the sweet spot for resistor biasing an op amp is to use kilo ohm size resistors for practically everything. Okay. All right, that's enough out of me for today. So what we're going to talk about on Friday will be an introduction to positive feedback systems and then some applications of positive feedback op amp circuits.